Yeah, and then if I forget to turn the camera too, you can notice that Steve will remind me to turn the camera like right now. Yeah.
Dr. What
What did he do?
He made it.
There's many ways. As you see, there are many solutions to the same problem. Anyway, so when you have this is number 4, homework 3. If you write, you have a positive number. You can write it as its prime power decomposition like this. This is useful. I mean, it follows from the fundamental theorem of arithmetic. You can assume that the primes are in increasing order. And in the fundamental theorem of arithmetic, it just says that there's a unique product of primes. It doesn't say that they're unique, like distinct primes. So in the fundamental theorem of arithmetic, you could have 100 primes, and they could all you get many repetitions of the primes. But in this, if you write it like this, you can assume that the primes are in increasing order, if you like. It makes your proof easier. So I assume that my integer had used the prime power decomposition. So if a is even, then the first prime number, the smallest prime number, will be 2. So if this is even, then this is 2 to some non-negative power, and then the rest of them are odd. All the rest of the primes are odd. So this is an odd number. And if a was odd to begin with, then you just put a 2 to the power of 0 up front. And so that's what pretty much everybody says something like that. Okay. But I probably should have left out the word uniquely representable, because the uniqueness comes from the fact that you can write it uniquely in this as a product of primes, and it's unique up to the order of the primes. Okay. Any questions about number 5 or anything else 1 through 5? All right. So on the back, everybody did fine on number 6, number 7. So I mentioned that for number 7, for example, 12x turned into 9 mod 6. We showed after last week's class that a linear congruence has a solution exactly when the greatest common divisor of this number and this number divides this number. So the greatest common divisor of 12 and 6 is 6, and that does not divide 9. So 6 does not divide 9, so therefore there's no solutions. And so that's kind of a more sophisticated way to do it. But like I told you, just try to solve it, and you get a contradiction, right? You get like even. Well, this is 0 mod 6, and 9 is definitely not 0 mod 6. 9 is 3 mod 6, so 0 can't equal 3 mod 6, and so on. Number 8, I also, I kind of purposely tried to present a solution that's different, just to give you a different kind of look at how I might prove these statements. So everybody knows that an odd number looks like 2 times an integer plus 1, right? So if n is odd, then it's pretty common to write n as 2k plus 1 for some integer. But it makes it a little bit harder when you're trying to prove this statement, because it's not a statement mod 4, it's a statement about mod 8. So when you square this, it's easy to see that it's one more than a multiple of 4, right? But it's harder to show that it's one more than a multiple of 8. So what I did, I said, well, if n is odd, then n has to be either 4k plus 1, or n is 4k plus 3, right? So if you use those cases, when you square those, it's a lot easier to see that they're 1 mod 8. So I just did 2 little cases like this, just to show you that another way to think of odd numbers, that they're also congruent to either 1 mod 4 or 3 mod 4. Is that clear? Right. I mean, there's only 4 residues. It can't be 0 mod 4, because that'd be even. It it can't be 2 mod 4 because that's also even. So every odd number has to be either 1 or 3 mod 4. Okay. And then number 8 is there's actually a deeper theorem for number 9. If you use the binomial theorem, you can see that if you multiply out like a plus b to the power n, that'll always be congruent to a to the n plus b to the n mod n. Because when you expand the binomial here, all the intermediate terms are divisible by n. So they're always going to just cancel out when you divide by n. So any questions about the problems? There was a couple of things that I saw that I wanted to also comment about, just the techniques of proofs. And I'm wondering if it's kind of just, we're a little bit new to congruences, but it's also, there was kind of a logical error that I wanted to point out in some proofs for number 7 and number 8. So, let me give you an example. So, if you have a statement like number 7, sorry, this is number 8, number 8 and number 9. So it says, if n is odd, then n squared is congruent to 1 mod 8. Okay? So what I saw a lot of people do is say, okay, well, let's assume n squared is congruent to 1 mod 8. If you're doing a direct proof, you can't do that. You can't assume that the conclusion is true and then, like, just kind of, it's kind of back to when I mentioned about like proofs by induction. You want to build up to this statement. You just don't start off by assuming it's true. What I think would just with a little bit of tweak to your proofs, it would be okay. What you're really trying to say is this statement is equivalent to some other easier statement. So if you instead of saying assume this is true, just say n is congruent to, so we see that n squared is congruent to 1 mod 8. You could say if and only if, either use a symbol like this, a double-sided arrow for if and only if, or just write if and only if. So this is true if and only if 8 divides n squared minus 1. Right? So this is true if and only if this is true. So if I could prove this, that's the same as proving this. But this is true if and only if n squared minus 1 looks like 8 times an integer. Okay, so I saw a lot of this going on, that people were saying, well, if this is true, then this is true, and then this is true, and this is true, and then since that's true, therefore that's true. But that only works if you have if and only if statements on each row. Because if you left it like this, and said, well, this is true, that means this is true, and that applies to this is true. Well, I can show this is true, so therefore this must be true. That doesn't work because you don't have the reverse implications. So all you really have to do is just add the other side of your arrows. Some people use arrows, or some people just left off, didn't write anything. And I think you're applying the if and only if statements in your proof. Okay, so if you want to do that, that's fine. And then, so then we know that n is odd. So we know, n is odd, right? So then a lot of people wrote, replace this with like 2 times an integer plus 1. So let's say 2m plus 1 squared minus 1. Or let's just say up here n equals 2m plus 1. And then, so you're getting easier statements to prove. And then the last one was like obvious. It was like, well, I guess there's still a little bit of work to do, I guess, right? point is, if you're gonna start with the statement you're about to prove, you can't assume it's true. You could say this is equivalent to this statement. That's what the if and only if statement is saying. This statement is equivalent to proving this one, which is equivalent to proving this one, which is equivalent to proving this one. And so then you get it down to a much easier form. And then once you've shown that, then you can go back and say, okay, therefore this is true. Okay, so I saw that a lot with question number 8 and number 9. You can't start out by saying, okay, let's assume this is true, and then show what that implies, and then say, well, since that's true, then this is true. All right. That's just a little. It's a little thing, but it makes a big difference, right? I mean, logically, you can't go back up the page if you don't have these reverse arrows. Any questions about that? So if you see a bunch of IFF on here, that's what it means. It's a if and only if. I couldn't do a double-sided arrow very easy on the PDF, so it's if and only if and only if and only if. Those mean the same thing. So you either one of the, you can do the arrows or you can do if and only if. So this is true if and only if this is true. If and only if this is true. If and only. It's called a biconditional proof. You're proving in both directions at the same time. Okay, any questions about homework 3? And like this one, number 9. You could just I'll just start with this. Just start with this, and then you end. It's really, if you look at my proof on my page, it's just not very long. You just say, okay, a plus b cubed, that's a cubed plus 3 times a squared b plus 3 times a b squared plus b cubed. And then this is 0 mod 3, this is 0 mod 3, so that just equals a cubed plus b cubed mod 3. And that's really all you have to say. So again, you don't want to start off saying, well, let's assume that a plus b cubed is congruent to a cubed plus b cubed. And then you can do that if you want, but again, if you want to start that way, you would say a plus b cubed is congruent to a cubed plus b cubed mod 3. Then you would say if and only if, and some people use the definition of congruent, which is fine. So if and only if 3 divides a plus b cubed minus a cubed plus b cubed. And so, again, you could do a chain of if and only if statements, and then the last one I think was pretty obvious, like 3 divides some multiple 3. So you say, well, since the last one's true, therefore the original one's true.
Doctor, sorry. So do we, like you said, since this is 3a squared b and 3ab squared is both 0 mod 3, then we can go here. We don't need to say that in our proof?
If you...
Because I have a lot of sentences.
You might say that. You would say, this equals this since this and this is 0 mod 3. You could do this, and you could just, to really show that,
Because like after that step, I went to, we know that I factored out a 3 in both and then said that whole middle equals 0 mod 3. Right. So inevitably I did, I just wondered.
Yeah. So you can, right, and that's the key to proving this, that you got to realize that this, if you want to leave it in congruences, the key to proving it is that you can always replace any integer with its residue. So 3 is 0 mod 3. So this is just 0 times this, 0 times that. So those terms just are 0 mod 3. If you convert it back to a statement about divisibility, it gets a little bit more complicated. If you just leave it in congruences, it's more is better. More explanation is better.
I know this doesn't pertain to this example, but let's just say there was a 4 in front of the a squared b instead of a 3, right?
Yeah.
Could we automatically replace that with a 1?
Yes.
We can't.
Yeah.
Okay.
You can replace it with
even then, because we're dealing
any
reference is not necessarily algebraic equations. Gotcha.
Right. Okay. This is modular arithmetic. That's the benefit of of modular arithmetic, you can always either simplify or change an expression the way you want it to look, as long as you're following those rules. You can, you're basically when you change when you're changing a 3 to a 0, you're adding or you're subtracting something that's 0 mod 3. I mean, so that's why it works. That you can always just replace any integer with its residue. Yeah, so I mean, and that's the way you guys solve those congruences, like on number 6. I mean, you're getting more used to that idea of replacing any integer by its residue to make the equation easier to solve. Right? Like it was number 6, like there's a 9x congruent to 8 mod 7. So some people I saw kept adding multiples of 7 to 8 until it was divisible by 9, which is fine. Some people subtracted 7 from 9 and wrote this as 2x mod 8, and then now you see you can divide both sides by 2. So that's the way I thought it was the shortest path. So you can do it. You can always replace. I mean, you could have written this as 1, and then I don't know. I mean, so you can play around with it, but there's many ways to solve these. That's kind of why some of the proofs I gave, I wanted to show you some proofs using modular arithmetic instead of like undoing divisibility statements and converting it back to a divisibility statement. So, any other questions about homework 3? Okay. Then about homework 4. Anybody got any questions about homework 4? Anybody looked at homework 4 yet? So one of you guys, I mean, I know it's kind of, you guys had class last night and then class today all day, so you guys wait till, a lot of people submit their homework on Wednesdays. I mean, so you guys do most of your work on Wednesdays, or?
Can I turn it in today?
Rather than anytime, yeah.
Rather than on the internet? Okay.
Oh, you mean
rather
in person?
It, yeah.
That's fine. Yeah.
Okay.
And if you guys are on campus, it would be easier. There's the copy machine in the math department. You can ask Heather over there, the secretary. But it's already set up to email directly. You can scan and email it to me real quick, and it makes it it's real easy. If you have, I mean, some people don't want to tear it out of a notebook. You don't have to. You can just scan each page and then email it to me. So if you're on campus, that might be a quicker way to get your work scanned. But I can't stick around too much after class today. So if you plan on just like dropping off like after your 2 o'clock class, I won't get it. So, but that's the easiest way to do it. If you're on campus, you want to email it to me. Nobody told me.
Question.
Yes.
For homework number 4.
Oh, yeah, I just switched it. Yeah, I switched it there. Okay. Sorry, let me erase this and then we'll talk about it. I got it off track there. So, homework 4, yeah, so that's what I want to talk about now. Yes.
Number 7, the second one down says 4x is congruent to 6 mod 14.
Yes.
Okay, and I understand that you, so that gives you, if you come down to x is congruent to 5 mod 7. We keep the mod 7, right? We don't change back to mod 14 when we go to solve that.
Yeah, so, right, so the problem with, number 7, it's a little bit more complicated than the one I did in the lecture, and then you're on exactly on the right track. It's easier if you solve these for first, so you get a coefficient of 1 here. I mean, I gave you the general statement of the Chinese remainder theorem, and so you have to find inverses of all these guys and so on. So it is easier. It's easier if you simplify first. So you said you get 7, that's what you did, so we divide by 2. So since 2 is not relatively prime to 14, and that's why you have to drop the modulus, right? And then, so if you solve this one, so I solve all 3 first, get x by itself, and then use the like follow kind of like the example I did. I give you 2 techniques for solving the Chinese random thing. Either way is
yeah. Our question was that if you change it to mod 7, you leave it as mod 7 and you go to solve. You don't change it back to mod 14 to solve, correct?
Right. Well, yeah. So you'll get a solution because it'll be your solution will be a solution mod 5 times 7 times 3, but that will still be a solution. If you get x is congruent to, I don't know what the answer is, but say 2 mod this number. But it'll also be congruent to 2 mod 5 times 14 times 3. I mean, because if it's 2 more than a multiple of this number, it'll also be 2 more than a multiple of.
So when we go to do our answer, you want us to leave it with 7, even though 7 wasn't one of the original mods. Or it's okay to do that.
You can.
It's okay to leave it in a mod that's.
Yeah, because you're basically when you leave stuff. So when you solve a congruence and you leave the answer like x is 2 mod this number, there's actually an infinite number of solutions. So it's just 2 different ways to write that infinite
so
set.
you don't care which way we write it.
No, I don't mind.
Okay,
That's fine. So because you're saying these are all numbers that are congruent to some number mod this. That's an infinite set.
Well, I think what brought the question up is she did it one way. She reduced it and left it as 2 mod 7 or whatever.
Right.
5 mod 7. And then because in one previous example, you multiplied the mod back. Mm-hmm. And so I did that in the Chinese remainder theorem. And I got a different answer. My answer worked, but it was a different answer than hers when I left it as mod 14.
You get a different answer mod with a different modulus.
With a different modulus.
Yeah, so it could be the same sets.
No, it was a different remainder.
So you're saying so they're not.
Well,
you're saying your numbers aren't congruent.
Mine reduced because my mod was different. Never mind. You got 187 mod 210. I got 187 mod 105, which is.
So, you're describing the same infinite set in 2 different ways. Right?
That was one question I had. Like 187 mod 210 compared to 187 mod 105, right?
Yeah, that's the 2 answers.
Wouldn't the mod 105 have one element that's less than, smaller than the mod 210?
So we're asking if these are the same sets?
Yeah.
So I mean, I would write this as
that would be at least 82 mod 105, right? Now, wouldn't that would contain 82, right? Correct? The number 82. But the modulus above is a set that does not contain 82.
But every number here is going to be 82 mod 105. Every number here, see what I'm saying? You can't compare a number mod 210 to a number mod 105.
Yeah.
And you have to.
But so those sets aren't equivalent, correct? Because 82 mod 105 would contain all of the elements of 187 mod 210, correct? And then it's more than that.
Okay.
You see what I'm saying? That's what got me. 82 mod 105 would contain all of the elements of 187 mod 210.
Right.
But it would not be the same in reverse.
Yeah. So
that's what got
these
me.
Numbers. So I guess so. There might be more numbers in this set. You're saying so, but the way the Chinese remainder theorem works is you have a unique solution mod this number, and so that would be, I guess, is the unique solution mod this number.
For that.
Okay, but you could also have a unique solution mod this number.
Gotcha. Okay.
Yeah. And the issue was that I gave you a congruence that could be simplified. So maybe in the future.
Well, we simplified it, right? I just changed it back to mod 14 because, like, on number 3, why do we do that? Because you did it in an example in the video, like for number 3. Was that, and we started debating that was because we had to get the 3 solutions.
Right.
That's why we multiplied it back. So for the Chinese remainder.
If I just said find an integer that solves the congruence, I mean, you don't have to convert back. But if I say find a complete set of mutually incongruent solutions, you couldn't leave it like this. I mean, because you could you have to go back to the original modulus and find all the residues that satisfy the original statement. So this homework I'm looking at is it's more computational, right? I mean, there's only like one, two proofs, number 4. So.
The only question I had, one more, is on number 5. When you write that inverse, what's my final answer?
Yeah, you can just say,
I know it's 4.
Okay, well, let's not give it all the answers.
Sorry.
Let's say, for example, if it was 4,
If it was 4.
you might say, you can say 4 equals 7 inverse mod. What's it, mod 9?
Okay, so it is an equal, not a congruency. Is that more? So it is an equal, not a congruency?
Yes.
Or is it
Both?
either one?
Either one.
Okay. That we were debating on.
Because what if I if I multiply, so 4 is the inverse of 7. That's because 4 times 7 is 1 more than 1 9.
Yeah.
So if I add 9 to this, you get 13. It's 13 times 7, 1 more than multiple 9.
Be 91. So yeah.
So it's congruent, and it's also equal. So there's more than one way to write it. It's just usually you write the least positive residue. Like 9. That was one of our debates. Yeah, I mean, what's an extra line? You get, like I said, you just get used to it. And you don't even. It's like, do they mean incongruent or equal? I mean, I mess up. I catch myself saying that, like this equation, and it's really a congruence, or I'm speaking on the video. So, okay. Anything else? Homework 4. So, I mean, I don't care if you have the solution. I mean, you guys wouldn't just write that on the paper and try to turn that in, right? Because you just explain why 4 is the inverse of 7 mod 9. It's mostly to determine if you understand the idea of definitions of an inverse. Let's see. Any other questions? Okay. No. Question? So, has anybody ever heard of casting out nines? Anybody heard of casting out nines? You guys?
I don't remember what it was, but
You remember hearing of it? Yeah. So I heard about it about 10 years ago. It was casting out nines is a technique that even elementary school kids were taught to check arithmetic, but kids don't do any math anymore. Especially in elementary school, right? No. So just use your calculator, right? You don't need to know how to add and subtract large numbers to get a calculator. But so the casting out nines was a way to. The basis is using modular arithmetic, and so I'm going to talk about that. What's interesting is when I was doing some research last night, apparently this process of casting out nines was known as early as back in the 3rd century, and some other things. There was Gottfried Leibniz, who was credited, one of the inventors of calculus. They claim that he used it quite extensively. So if you think about calculus, there's a lot of, back in 1600s when Newton and Leibniz were doing this, they're doing all these calculations by hand. There's a lot of arithmetic, and so you want to make sure you did things correctly. And so using this idea of casting out nines, and so I'll show you how to do it, but it's just you check things mod 9, and you check them 2 different ways, and if those numbers match up, then you likely did your calculation correctly. There's still like a 1 in 10 chance you did it wrong, but like it's if I guess it's just because things can be. If you're off by 9, then you're still going to be it'll still be look like it's congruent mod 9, right? So if you make a big mistake, but so let's see. Here's the idea. Here's a kind of a starter problem here. Okay. 117,645 mod 9. Seven. Right? I just casted out nines to figure that out. So what I did, the 4 and the 5 gives me 9. So I cancel the 6, the 2, and the 1 gives me 9 when I add those digits together. And so the only digit left is 9. So that's the idea. So you guys heard this before probably, right? Like if the digits add up to 9, then the number is divisible by 9.
Yes.
So that's the same idea. That's the same as casting out nines. So this number is 7 mod 9. So why is this true? You ever thought about that? Why is a number, if the number's digits are divisible by 9, why is it also divisible by 9? So let's write this, kind of break this down each digit. So the 1 is, think of that as, let me start over. So the 1, this is 7 mod 9. So 1, 7, 2, 6, 4, 5 is 1 times 10 to the 5th power plus 7 times 10 to the 4th power plus 2 times 10 to the 3rd power plus 6 times 10 squared plus 4 times 10 plus 5. So, if I'm going to reduce this mod 9, what should I replace 10 with? Mod 9. 1. So 10, so the reason why this works is because 10 is 1 mod 9. So this just equals 1 times 1 to the 5th plus 7 times 1 to the 4th plus 2 times 1 to the 3rd plus 6 times 1 squared plus 4 times 1 plus 5 mod 9. And so equivalently, that's just 1 plus 7 plus 2 plus 6 plus 4 plus 5 mod 9. So if you want to divide an integer by, if you want to look at an integer mod 9, you just have to add up the digits. And this works again. The reason this works is because 10 is 1 mod 9. And then, I casted out 9, so 5 plus 4 is 9. Well, that's 0. That's 0 mod 9. So that's why you can cast out the 9s or get rid of any digits that have the 9, because this is 0. This is 0 mod 9. Right? And then the 7 to 2, that's 0, or whatever that is. Yeah, whatever. So 6 and 6, you just get 1 plus 6, so you get 7 mod 9. Okay? So now you know why. If a number's digits, if you add up the digits of a number and it's divisible by 9, and in other words it's 0 mod 9, then the original number is 0 mod 9, or divisible by 9. Okay? The reason this works is because 10 is 1 mod 9. So this is, I'll show you how this was used to check arithmetic problems. Alright, so again, this works. Because 10 is congruent to 1 mod 9. So let's talk about casting out 9s. So say I want to add these numbers. 3,264, 8,400, 2,146, 3,206. So you give this to a first grader in 1905, and he would add it up. And 17,831. And then he wants to check that his arithmetic is right. Okay? So what we're going to do, we're going to really, you want to look at each one of these summands mod 9, and then look at the total of the sum mod 9, and when we add up all the residues mod 9 and look at the residue mod 9 here, they should be the same. And if they're not the same, that's how you check that you did there's a mistake somewhere. Okay? So we're going to cast out, when we say cast out 9s, so like I see that 6 and 3 gives me 9, right? So I can kind of get rid of the 6 and the 3, that's 9. So I'm left with 4 plus 2. So this would be 6 mod 9. Okay. 8 and 1 gives me 9. 4 and 5 also gives me 9. So this number is 0 mod 9. Here 9's gone. 6 plus 4 is 10. Plus 2 is 12. So 12 is 3 mod 9. 6 plus 3 is 9. So I have 2 mod 9. And then I'm going to add these up, and so I get 6 plus 3 is 9, and so I should be, so I get 2 mod 9. So that's my check right here. So this answer better be 2 mod 9. If it's not, that would be a quick, and so, you know, once you're used to doing this, you can do this pretty quickly. And so it's a quick way to check your arithmetic. So is this 2 mod 9? Yes. So you cast out a 9 here. So 7 plus 3 is 10, 11. So this is 11, which is congruent to 2 mod 9.
Couldn't you cast out 9s from all of the four-digit numbers interchangeably? Couldn't you couldn't you combine, like, let's say the 3264, right, has a 4 in it.
Right.
Take that 4 and see if there's any other numbers.
Anywhere in the...
Yeah, anywhere in that array.
Yeah,
Cast out 9s in that entire array.
You're basically like adding all these digits together and just like we did here. Like you just add all the digits together and...
So you technically cast out...
Okay, I see what you mean, yeah.
You can cast out any direction.
Yeah, you could... So that'd be a better way to do it probably, right? So you
Can
could
you cast out leave over?
Sorry?
Can you cast out, like, can I take the 4 and the 4 and take one of the ones from the 2?
That's what I was
Yeah, that's
saying.
exactly what he's saying.
Okay,
So
okay,
like, so
you
is
don't have to
there...
match exactly.
Let me do this again. I don't want to, it's going to too complicated with all these, to see what we're doing. Because I don't want you to look back at your notes and say, like, I don't know what we just did. We just see, okay, it's like it's 2. All right, so, clearly. So just anywhere you go, like an 8 and a 1. Oh, I'm chalk. 9s. So like 6, 3. Do you see any other ways to do this? Yeah. See, I don't want. I mean, I don't start putting more numbers back in. So once you get rid of them all.
So you can add up and get 18.
Yeah.
Where?
You get 18.
2, 4, 4, 6, and 2.
So 10. And then
2, 4.
And
And
then
then the
2
bottom.
2s and a 4.
Yeah, I like that.
all right. So the 2's on. Yeah. Okay. I like it. Yeah. So you get the idea though. It's a check. Apparently this was taught to like elementary school kids, and they didn't explain to them the modular arithmetic. They just explained the process to them, and then the kids could do it quick and check their digits. And so they check to see if they get these two right, and then they know. Now it doesn't guarantee they're right? Like if you wrote
840. Yeah. If you put 840.
Sure. Yeah. If you off by a multiple of 9.
Yeah.
Depends.
Which happens when you transpose numbers.
So if you transpose, but if you transpose, it wouldn't affect the. Yeah, you're right. If you transpose, you still have the same modulus, and then if you guys ever done data entry, that's one of the common mistakes. Like if you ever enter data and you're off by a multiple of 9, that's probably what happened. Two numbers got transposed. Because you still have the same number mod. It's still congruent mod 9, but it's a different sum. So this is called passing out 9s. If you want to, you could write a theorem to describe what this phenomenon So if you have an integer, and so the first digit is a to the n. So a to the n times 10 to the power n. A sub n minus 1 to the power of 10 to the n minus 1. All the way down to a1 times 10 plus a0. Okay. In other words, you have a number, and the digits of the number, the one place is a0, the tenth place is a1, and so on. So those are the digits of this integer a. Then a is congruent to an plus an minus 1 plus a1 plus a0 mod 9. Okay, and the proof is exactly what I just erased. Essentially, you start with this, and then you replace all these guys, all the 10s, with 1, and then that just simplifies to this. I mean, it's not really, I don't really need a proof, but let's say proof. So if you have any one of these terms, ak to the 10 to the k, that's going to run to ak times 1 to the k, which is going to ak mod 9. So when you add up all the terms like this, each one of these terms just is congruent to the integer out front. So that's called casting out 9s.
Why does that work with 3s?
Why does it work with 3s? Maybe it's a homework problem coming up.
No. Now I've got 22 people after me.
Well,
It's the same thing.
so you'd have to, prove a statement. So look at this. So
Never mind, I got it.
you see why?
Yeah. You can get up for homework problem now.
Here's the proof.
Sorry. It doesn't be a homework problem now.
So you see why though?
Yeah.
Because 10 is
1 mod
3.
I guess thinking, well, I guess you wouldn't know that. Never mind.
Then I wouldn't know something.
Not from a million years ago. I was saying, why did they teach the kids the 9s then? Why did they teach 3? 3 is a smaller number. Why did they teach them casting out 9s? Why did they not casting out 3s?
Because you'd have, like here, if you made a mistake, you'd have your mistakes would have to be differ by 9. I don't know. Maybe
The chances that your two numbers are going to sum up to 3 is less
Yeah.
likely than summing up to 9.
I was just curious.
yeah, it's
Because like
When
so
you're
it catches more errors, I think, than mod 3. It catches more errors. I mean, so
Well, the biggest
There'd be-
digit you can have in
there'd
each
be
number.
90%, like 1 out of every.
you have to add up to multiples
10
of 3 rather than just adding up to 9.
That's only three mistakes. 1 out of every 3 mistakes.
It's kind of like in that last one where we said all those numbers add up to 18, but you have to do that in a bunch because you're going to have to add up to multiples of 3.
Well, there's just not very many elements of mod 3.
Yeah.
Yeah, that's right.
All right. let's take a 5-minute break, and we'll, let's just start back at 10 o'clock. It's like, I'm just gonna leave the camera rolling. So.
Yes.
Yes. You see Coleman and Books.
That's just my personality. I hide it.
What I want to say is,
If you just follow what he does or finish what he starts, I'm okay. You have to start it.
No, I just hide it. That's my personality.
I just don't know where to. I don't know.
it's probably.
I'm not very good at writing.
It's kind of like every you can do it.
Pretty much.
Yeah, I want to see.
Well, to be correct,
I just started I think it's video.
I have 3 of those.
Because at 1:30 last Jesus, where I realized I was just writing. I wasn't actually absorbing anything from the video.
Shut down.
Yeah.
I seriously just hit me like some. If I had paid attention to what he said, I've just been writing.
The only thing I get is.
Doesn't have. I can't even like how you say.
What's he doing?
I don't even know, like, that's like search for what she said was the definition.
I put a few of them.
Yeah.
Okay, well, it says that.
I have a hard time
There's one
finding it.
down. Keep going straight down, yeah, you'll see it. Yeah, I don't have much experience using it, but like, again, if you were presuming that you didn't just transpose, I mean, it's hard to transpose, I think. So the only mistake that ever occurred is if your total answer was off by 9. Yeah, exactly. So like if you put,
In regression, actually.
I mean, it'd be a pretty bad mistake, because I mean, we off by 9.
I thought we were doing
You'd have to,
Yeah.
Yeah.
no, so it's the problem is that it wouldn't catch the error if it's, because there's, you have a total of 10 residues, and if both residues are 2, then it wouldn't tell you that you made a mistake. So in other words, like 1 out of every 10 residues is right. If there was a mistake and the residue was still 2,
I guess
it
my
wouldn't show
motion,
it.
I see what
This is just that class.
Can you admit it out loud?
I hope cross keys 3 times today, so my backpack, I know, got a backpack on, so I know it's from.
That's a good one. You're showing that then if you can prove this, then so that's exactly that's another way. So you either I feel we're saying if this then this. This is true. Yeah, that's not exactly the.
Have you proved the modulus?
The subtraction?
But you see, you subtract, and then the sum of the place values of the subtractions. Same number scrambled.
Right.
So, yeah, the subtraction of the transposition gives you a multiple of 9.
Okay.
Can that be proved with modulus?
Sure.
Because the way I've seen it proved is this, right? There's always some borrowing rule. This would become C plus 10, right? This would be B minus 1. And then when you subtract, you got C plus 10 minus A, B minus 1 minus B, A minus C, and you got 9. That's how I've seen it done before. It always equals multiple 9. Because if you want it twice, if you look at this reason here, this digit cancel out, you're always 0 mod 9. So then you're left with. I see. It's always 0 mod 9. It's always 0 mod 9. I see. When you're subtracting the A,
Well, and that's another thing
You just have you have all these pluses, and then below you have all these minuses. So
yeah.
0.
Mod 9. Yeah, because you just rearrange it and you just get 0 mod 9, which means that it's going to be multiple 9. Okay. See, I
teach the concept.
done it that way. But then here you're still assuming that all multiples of 9 are summation of 9. You know what I mean?
If the answer is a positive number, then you keep going down and down and down. Eventually you get back down to 9.
With the highest grades,
I see.
and I showed a type sheet.
So what do they have? What do they do? So there's another trick I wanted to show you.
So they say 5, right?
I like my analysis.
Now you can't say I didn't use this book in class.
I like it a lot.
So I didn't mention this in the syllabus, right? This is more for a reference. I'm not going to be following directly. So in page 13 of this book, it says in the first paragraph, one of my favorite quotes says, okay, let me read the last 2 sentences. It says, the variety of proof techniques sometimes seems so large that students regard number theory as a bag of tricks. But of course, this is a matter of familiarity. What is a trick the first time one meets it is a device the second time, and is a method the third time. So that's, I often misquote that. And you see, it's a trick at first, and then you see it, you do it over and over again. Now it's a method. It's a technique that you use over again. So maybe you felt that way in some of the proofs you're doing. You see, it's not really a trick anymore. But here's a new trick. So here's a new trick for you. Bag of tricks. What if I change the modulus in this theorem to 11? So recall that the casting out 9 work because 10 is 1 mod 9. So when you add, if you have a number like this, it would be congruent to all just the two.
Negative one.
One.
So now 10 is negative 1 mod 11. So you see what happens in each one of these terms, you replace this with negative 1. So what's going to happen is instead of adding up all the digits, they're going to alternate plus and minus whether or not you get negative 1 to an even power or negative 1 to an odd power. So you get negative 1 to the n plus down to I'm going to write that the second time. So a to the n minus 1, negative 1 to the n minus 1. So you're just replacing all the power to 10 with negative 1. So it's a1. Let me just put it this way. Negative a1 plus a0. Okay? So the proof is, and you take any one of these terms, so a sub k times 10 to the k, this will just equal a sub k times negative 1 to the k mod 11. And so it depends on whether k is even or odd, right? If k is even, so if k is even, so negative 1 to the k equals 1, and if k is odd, I don't have to really write this out, but I mean, that's the idea. So negative 1 to the power k will be congruent to negative 1. So in this congruence here, the terms are going to alternate plus minus, plus minus, plus minus. Okay, so the first, the a sub 0 is going to be positive, then the next one's going to be negative. So it might be easier. I mean, it's hard to write. I don't know. I didn't say. I know it's even or odd. But so a similar trick works when you're dividing by 11s. So let's look at some examples. So since 10 is congruent to negative 1 mod 11, we'll see that 10 to an even power is going to be congruent to 1 mod 11, and 10 to an odd power is going to be congruent to negative 1 mod 11. So let's find 1, 5, 2, 3, 4, 7, 8, 3. Reduce this mod 11. Okay. So it's similar to the casting out lines, but instead of adding up all the digits and reducing mod 11, you have to alternate. So this is going to be plus, minus, plus, minus, plus, minus, plus, minus. So instead of adding them up, this would be congruent to negative 1 plus 5 minus 2 plus 3 minus 4 plus 7 minus 8 plus 3. So let me do so 5 plus 3 is 8, 7 is 15, 18 minus 1 is 8, minus 3, minus 7, minus 15, minus 15. So this should be congruent to 3 mod 11. And it is, good, that's what it says on paper. So it's a similar trick, right? So instead of, and the proof is right over there, right? So you could break this up as 3 plus 8 times 10 plus 7 times 10 squared plus 4 times 10 cubed and so on, and then you would reduce each of those powers of 2 to either 1 or negative 1, depending on whether the exponent is even or odd. Okay. Any questions with that? quiz time. No, not really. So, pop quiz here. I want to see if you can answer this question. This is not for grade. It's just I just wanted to see if you can apply these two tricks. So this is it leads to the concept of a check digit. So check digit I'll talk more about in a second. But oftentimes when there's numbers, which think about how numbers are assigned to everything in our society, that you have like all these numbers on your drinks and things that scanning these UPC codes. So everything has an identification number. You guys all have an identification number. So if you can check, a check digit is used to verify that the number is in the correct form. It kind of checks to make sure nobody inputted made error when they're inputting data. So this is the idea, kind of defining this question. Now we have two ways to check a digit. Suppose you have an integer like this: 1, 3, 6, 1, 2, 3, 4, 4, 5. You're missing a digit. We have a long integer, and I'm missing the digit x. Okay? First question. If n is divisible by 9, then what is x? What digit must x be if this number is divisible by 9? You guys cast out your minds?
Yeah.
Yeah. So, right. So we know if this is divisible by 9, then this is congruent to 0 mod 9. Right. So we know that n is congruent to 1 plus 3 plus 6 plus a bunch of zeros plus 4 plus 5 plus x plus 0 plus 0 plus 0 plus 4 plus 1 plus 4 plus 2, made long numbers, plus 7, 7 plus 2, mod 9. Right? So now that's where the casting out 9s comes. Anything that's 9 is 0 mod 9. So the 3 and the 6, the 4 and the 5, the 4 and the 1, the 2 and the 7, the 7 and the 2. What's left?
1 plus
So x and in the right order. So 1 plus x, but we know that all should be congruent to 0 mod 9.
This is 8.
So x is 8.
Yeah.
It can't be. No, it can't have a negative 1. Yeah. So x is congruent to negative 1 mod 9, but the only digit that's congruent to negative 1 mod 9 is 8. So this is the idea of a check digit. If you had a long identification number, you could quickly tell if there was a mistake because whatever however you calculate your check digit. Like in this case, the check digit would be 0. You'd say you might have a long identification number and then the last digit would be 0. And so the computers or whatever, the scanner that reads things, they know that that's the check digit, so they do some operation with these numbers, and if it doesn't equal 0 mod 9, then there'll be a red flag, like some mistake here. Okay, so we know every integer. If I'm assuming this integer is 0 mod 9, then we can determine that missing digit. Okay. Any questions about that? I'll erase this. I don't have to write that number yet. Alright. So if, which is X there. If n is, let's put it this way, n congruent to 5 mod 11, so what is X?
6, right?
You said 6? I didn't get 6. 9? I didn't get 9 either. Doesn't mean the answer's not 9. I didn't get 9.
Is it 5?
I didn't get 5. So neither. Yeah, I just kind of. The hint is it's either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10.
It's in there.
No, it's not 10. It's
Somewhere.
X is not 10 mod 11.
I give you a 9. I got 9.
3.
I guess it would be 2. It would be 2. Yeah. That's 46.
So,
Yeah, there's a 5.
you want to take a vote? So 2. What did you?
Oh,
you get?
the digit has to be
You got 3? Did you get 3 too?
The digit's 3.
I got 3 when I did it.
I forgot I was doing 11, that's why I
Ah.
Yeah.
But there's 2 left over, and you gotta get to my 5. This way. 5 left over.
So the idea is when you're doing mod 11, you don't add the digits. You have to alternate plus minus the digits.
When I switch the thing, add all that stuff, eventually get it down to.
This is number 1, part 2. Number 2. All right, so and we'll be going to -1 plus 3 minus 6 plus 0 plus 4 minus 7 plus x minus 0 plus 0.
So I have to have the
Plus 7
a 5 on it. Okay, so, and then you subtract.
I got a plus 2 and a minus 7. I got a plus 7 and a minus 7.
What we have here is really the 7 and replacing
And I got a minus 5. Whatever. So I'm getting. So what do you get? You get. I got. I got x equals 2.
Yeah.
Equals 5 model. Is that what you got? Yeah. So you got an x, and then all the other numbers add up to 2, and we're saying that this must be congruent to 5 mod 11.
Yeah, I'm trying to figure out where I'm getting stuff.
X plus 2 is congruent to 5 mod 11.
So X is 3?
The only digit that's 3 mod 11 is 3.
Okay.
So you would if you could quickly, you see how this is very programmable. You could program this in very easily. Enter any number, and you can find its residue mod 11, and that would be your check digit, for example. So if you're say you wanted to transmit a large long number over walkie-talkie, I don't know, you give positions of the enemy or something, and you need these digits to be right. So you give them a long number, and then you say my check digit is 3, and I don't know. So it sounds kind of far-fetched, but this is, imagine you have a Mars lunar rover or whatever over there that is submitting pictures back to Earth, right? So it just emails it to Walmart, and then NASA goes down to Walmart and prints out the pictures. That's not how it works, right? They submit these. I mean, it takes a long time for the data to get there, and it's all digitized in ones and zeros. So if you transpose, if you have a bunch of ones and zeros, and then there's a solar flare, and then I mean, wouldn't it be nice to know if the number that NASA got was actually the right number, right? So what you can, I mean, there's ways it'd be important to have like check digits or some kind of system to verify that the long number that you had was correct. And so one way around this is you could, instead of doing it every 1 and 0, like right in order, you could do like, they could transmit 1,000 ones, or 1,000,000 ones. So 1,000,000 ones. And then 1,000,000 zeros, right? So, and then that way, so if you got some zeros in there, it would be, you could tell that there was a mistake. I mean, so there's other ways you can kind of read, but I mean, so think about everything is digital, and so everything is converted to numbers, and so this is used for credit cards. Have you ever bought anything online, and it says, oh, your credit card number is wrong? And you're like, really? I thought it's that. And they can, how do they know? Well, you might even have, maybe just one digit was wrong, but they can check, there's a check digit in your credit card number too. So if it's not in the right, if the check digit doesn't match up, then they know that you made a mistake when you entered your credit card data. And even like, so I don't know if you can look into this, but the number on your credit card, the first few numbers determine what kind of card it is. Like a 5 is MasterCard, things like that. So there's a number, and then there's like a bank number, and then there's an account number, and then there's a check digit somewhere in there. And there's some kind. I tried to look up the algorithm for finding it, but I wasn't finding. I was finding conflicting information about the check digit for credit cards. Another thing, I didn't want to give my credit card as an example. We're going to skip that one. So, but let's talk a little more about check digits. So you guys ever bought or sold anything? Bought anything in the United States? Or have you bought or sold anything processed? Or you processed anything that's bought or sold? Has anybody seen the movie Say Anything from the early 80s? So this is, I was thinking about all this, how everything is in our society has its UPC numbers on it, right? You have one on your water bottle there. You have these UPC codes. Everything has been processed or bought. This is an old movie. It's old. What happened?
Seriously.
Okay, so
Oh, that's the future.
the teenage
So is that possible with Diane for Cherise? Seriously. I'm totally completely serious. Oh, really? You got a career? I don't know. I've thought about this quite a bit, sir, and I would have to say considering what's waiting out there for me. I don't want to sell anything, buy anything, or process anything as a career. I don't want to sell anything, buy or process, buy anything sold or processed, or process anything sold, bought, or processed. As a career, I don't want to do that. So my father's in the Army, wants me to join, but I can't work for that corporation. So what I'm doing is kickboxing.
So you don't want to sell anything, process, or buy anything processed or process anything bought or sold, and what's left is kickboxing. So everything is, we have these UPC codes everywhere. Everything's processed, bought and sold. So UPC stands for Universal Product Code. I'm glad you guys all brought your universal product codes in for this demonstration. Just about everybody has probably UPC somewhere on them or near them. You can check this. So this, so here is a UPC code that was the closest one I found last time I put my this up. So this is a box I found lying on the floor. Here's the UPC code. The final digit is a check digit. Okay? It's a digit that's added so that when you follow the process, the sum should be congruent to 0 mod 10. So here's the process. So if we start from the left, just look at the numbers there to the, don't use the check digit. So if you look at just the numbers to the left, you're going to start in the first position and alternate, you're going to multiply these by 3. So I'm going to multiply digits in the odd positions from the left. By 3, and then add them with the digits in even positions, except for the check digit. So this sum plus the check digit should be congruent to 0 mod 10. Yeah. Okay. So that's the process to verify if the code that you're, let's say you're reminds me of something funny. You go to the grocery store, Walmart, whatever, that has a stock boy or whatever, puts the stock back on there. So I have a Facebook friend that on his job description, it didn't say stock boy, it said grocery replenishment specialist. I just thought it was funny euphemism for like Subways or sandwich artists and whatnot, or custodial engineer, janitor. Right, so, but every grocery replenishment specialist could be putting these UPC codes on and check that they have a correct UPC code using this technique. So using this, it'd be like 3 times 8 plus 4 plus 3 times 8 plus 1 plus 3 times 6 plus 4 plus 3 times 0 plus 0 plus 3 times 0 plus 0 plus 3 times 9. And then you add that, so then you add 8, and that should be congruent to 0 mod 10. So I get 110 when I do that. And that equals 110, which is congruent to 0 mod 10. So you got your UPC code. Now it's kind of, some of them are weird because you have all these lines, and then like sometimes there's a digit like way over here. Like on this one, the 8 was kind of like up higher, and then there was like the numbers down here. Yeah, and then there's like a little number up high after. That's the check digit. So this is the first digit, and then that's the check digit. So. Yeah, your last zero is the check digit. The first zero is part of the number as well. So if there's a number up high, that's still part of your UPC code. And then the last one up here, that's your check digit. So just start from, just start from left to right, use all those digits, and multiply the first one times 3, and then skip. And then when you add them all together, it should be 0 mod 10. Did it work? Anybody?
Yeah.
You're probably thinking mods are technically useless. No applications in the real world. And that's when number theory started out. Like back with the ancient Greeks, they weren't building skyscrapers in ancient Greece. They were studying mathematics just because it's really a religion. I mean, it was like Pythagoras. It was a religious cult to study these mystic properties of numbers. And then even when number theory started picking up in the 1600s, 1700s, it was still just all pure math. It was just math for the sake of doing math because it's beautiful. And now, like almost everything in number theory has a real world application. It's really amazing how everything's been digitized into numbers. There's all of we'll talk about, one of my big goals for this special, I want to talk about cryptology, or cryptography, how we write codes, how we transmit data securely. It's all based on number theory. I don't know if you've ever heard of that, but when you buy that credit card, something with your credit card, it's transmitted over the internet. How can you be sure that it's secure? And your credit card number has to be encrypted, and then it's safe while it's being transmitted over the internet. And the techniques that are used to encrypt it are based on the fact that it's really hard to determine if a big number is prime. It's really hard to factor really, really, really big numbers, like a 100-digit number. If you take a 100-digit long prime, multiply it by another 100-digit long prime, you get a really big number. It's going to be really hard to factor that. It can be done, but it takes a long time, and by the time you can factor it, that code's gone. I mean, the transaction's completed, and so that's why things are safe. It's all based on factoring large primes and using modular arithmetic. So that's one of my big goals. We'll talk about polynomial congruences, law of quadratic reciprocity, and then we'll hopefully get into some cryptography. Does anybody have any questions about that?
Actually, my geometry textbook has a problem where they do a check code like that, but they explain the process, but not the theory behind it. But it's interesting to see. Right,
they just say, well, it should always be a multiple of 10, instead of saying it's 0 mod 10. Yeah. So. Anybody have any questions about? Did you guys get to work? Yes. You did? So, trust your drinks must be not counterfeit. Water, counterfeit, not due. So, that's really all the content I wanted to talk about today. I kind of, it's kind of this. We got a 2-hour class here. It's kind of last week. I had just enough material for the whole 2 hours. I think we had more questions and so on. Is there anything else I wanted to say? I'm trying to think about. Is there any questions about anything I think of? I mean, go back to homework or format of class or. There's one other thing. Oh yes, I remember now. Okay, so. I'm technically supposed to have office hours, right? On my contract, I'm supposed to have 1 office hour a week during a summer class. The way this class is, it's different. We're not meeting on campus. It's kind of impossible it really, or pointless rather. If I'm in the room and like everybody's different places, So what we've decided is to do like an online office hour. And now I guess I've been neglecting that part of the class. I haven't, so I've never used these like online meeting software. So I just kind of played around with it a little bit this weekend. There's a thing called Google Hangouts. You guys familiar with this? Some people are not. Anybody used Google Hangouts before? So this should work well then. So to fulfill my obligations, I mean, I'm going to start doing this Google Hangout. So it's basically like Skype. You guys doing Skype or FaceTime? I don't know. It's something. So Google Hangouts is like, if you have a Google Plus account, it's like you already have this capability, and you have a webcam. You already have this capability, apparently. So I did it this weekend. I just clicked on it, and like I can invite people. I can put in emails, and then you get an email link, and you can click on the link, and then we could be all in the same chat room together. So the idea is, I guess, you can have like up to 10 people at a time. So just from the frequency of questions I'm getting, I don't think we're going to ever have more than 10 people at one given time. But maybe I don't know. I could be underestimating, because if I have this available, maybe you guys are going to be just want to be in the conversation too. So, well, I don't know. So I'm going to try this. So, do you think tomorrow would be a good time to have a Google Hangout hour, because we have homework due? I seem to be getting a lot, some questions. Hey, check out this homework, see if I'm on the right track.
Well, we've got 2 classes tomorrow as well. Oh, is that 2 classes tomorrow? Oh, no, that's today.
Yeah. Today's bad. You're on summer break, I can tell. I'm off on my days too. I'm like, what is today? I asked my 6-year-old, what is today? All right. So yeah, he knows. He knows the day of the month. I mean, he's a numbers guy too, so he likes it. But tomorrow I'm gonna have a Google Hangout hour. So let me show you what that looks like. Let's see if I can record this. I can't. I'm gonna pull it off the later here. This is one of the downsides of this room. It has such a small, you can't like project anything to the whole room. Not too far. Really take this. TV. There's an infinite number of TVs. Can I put a mirror in the mirror? Where's that? I think I can zoom out a little bit more on this. Huh? Come on. I thought it was zoom in more. Exactly. Anyways, so when I've only done this once, so bear with me. Try to log on to Google. Yeah, if you have Google Contacts, it's all. You have all this capability.
Yeah, if you already have Google account, pretty much have it.
Yes, I am. I'm trying to. I'm glad you're here. Actually, I'm trying to show them how to do Google Hangouts. I did it once this weekend, and you know the easiest way to get it. Get it started. So you do just log in a Google account. I don't have anybody yet, I'm just explaining to them what I'm trying to do. So I need them, we have to be friends with,
You'd be like, you're just like, but you can't keep in the circle.
otherwise I can send them an email, right? Because,
So like,
So it's not, I mean, you can build right because he expects a collaboration. He expects us to work together on that, so it's gonna be done.
I just wanted to, yeah, so if you have Google account, you can play around with this too. So I logged in on the Google account and then Google Plus account and find those links for Hangouts. And I will, so Dr. Mackin said there's a way to record these, I guess, so if I start a Hangout on air, then I can email to you guys, I'll send emails. Is that right? Alright, we'll figure this out. But the idea is, so it'll be a virtual chat room, but you have video too. So if you have your webcam, then I can hold up paper, I guess, and show you something. I don't know, just card tricks or sleight of hand. So that's how I'm gonna fill this hour of office hours. So I will look for an email. I'm just gonna send you guys an email. But let's figure out. Let's just set a time tomorrow, and I'll try to record this so if you can't be there, you can go look at it. Again, if it doesn't, the time doesn't work for you, just call me on my cell phone, send me an email, just like usual. Okay. I mean, I've tried to be available to you at any time, reasonable hours. You guys want to call me on my cell phone or email me. So what time should we? I'm pretty free. Pretty much most of the day tomorrow, so what time do you think would be good? Any takers, any suggestions? 1 o'clock. 1 o'clock? 9:30. Any World Cup games?
9:30, if you got something going on. 1 o'clock.
Today I want to go out swimming, I don't want to be sitting with people.
You don't have to. Like, say you're done with your homework 4, I mean, that's basically what we're going to be talking about probably. You know what I mean? You don't have any questions, you're not going to be missing. I'm just going to be like answering questions. But, so, you don't have to do this. I have to do this by contract, so. Do this for your benefit. It's my pleasure to be sitting in front of a computer for an hour. So, I 1 o'clock or some.
I like 11.
Earlier? 11? 11 to 12?
Early, but not too early.
Do we have to get out of our pajamas to do this?
If you turn your webcam on, just please be presentable. Everybody. So, like newscasters, they got shorts and flip flops on behind the desk.
You got a shirt on, you're right.
Yeah. I remember recording this. On YouTube.
It's gonna be on camera.
So, does anybody have time objections to 11 o'clock?
11 o'clock.
11 to 12? I gotta send myself an email. So, my goal today would be to figure this out and email you guys like a link, and then you can. I think you might have to download something. Because when I did it at home, I had to download like a plug-in app, well, I don't know, whatever. So, you might. So, we'll do Hangout.
Okay, I can have
Wednesday. The 18th.
So it's
From 11.
and then
If you want to, you'd rather just do one-on-one conversation, that's fine. You can email me or call me, my cell phone, not during this hour. Okay. Any other questions?
midterm information.
Midterm. So, my philosophy on the midterm is, you should be able to do the stuff we've done on homeworks and stuff. Some of the proofs in class that we've done in lectures are just too long and too, involved. But you should know how to prove statements about visibility, congruences, things that we've done in, so some proofs. You should, like, for example, know how to prove there's an infinite number of primes. You should know, just look at the level. The questions are probably going to be about on the level of our homework problems, and they're going to be all based on material we've done in lectures and on homework assignments. You're going to have to solve congruences. You're going to have to answer questions like stuff like this that we've done in class. So I mean, it shouldn't be. I mean, there'll be probably some problems very similar to homework problems. Some, using the same, based on the same material. So, would you like to address the class or something, or did you?
No, I just had a few people I needed to talk to, and I'm really
That's fine.
sorry.
No, that's fine. We're just kind of doing bookkeeping stuff here
Good.
at the end of class.
For my school class.
Will we meet here for the test or
I think back over there. I mean, there's enough room here, but we're missing. It's a little bit tighter in here. You notice? That's why I just thought it'd be easier to go back over to what is it? 109. Yeah. So let's just go. So it's in 2 weeks. Is that right?
Yes.
And the only material on the midterm is going to be up through this week. So I posted one video already this week. I posted homework 5. So I will post 2 more videos, hopefully later today is my plan. And so we'll have 3 videos this week and then the homework 5. And so that's the only material that's going to be tested on the midterm.
So 1 through 16?
Yes. Yeah. So midterm. So I would just go back and make sure you can do all your homework and exercises. Make sure you get the big concepts. So it's midterm. Didn't I send that on the email yesterday? So midterm, and it's Tuesday, July 1st. And the July 2nd should have been Independence Day.
Will there be?
Anyways, July 1st, so it's going to be on lectures 1 through 16 and homework number 1 through 5.
I don't remember.
I'm going to kind of continue to write exams I have in the past, and my students have found, that I write pretty consistent exam questions to what I do in homework, and so just look at your homework assignments. So, for example, short, like I say, shorter proofs for things like if n is composite, then it has a front factor lessons for that. I mean, that's several sentences, but it's the techniques are contradiction or direct proof. You need to know definitions to do these. Like, what does it mean for something to be congruent? It's a statement of theory or a statement about divisibility, or you can just use the properties of congruences. But then there's all the just kind of computational facts. Like, you should know how to evaluate the Euler phi function. Solve use a Chinese remainder theorem, for example, if that was a question on an exam. So one thing I didn't really emphasize is using a complete residue system to prove a statement. Like if you say I want to say that a certain congruence has no solutions, like I think we know that 6x congruent to 5 mod 4. We know that has no solutions, right? We said, you can say why. Well, it's true because greatest common divisor of 6 and 4 does not divide 5. But you could also just check a complete set of residues mod 4. Like plug in 0, 1, 2, and 3. So that's another technique that you can use to show that 6x is not going to go to 5 mod 4. Now, if you use a complete set of residues mod 4, you can show that no residue would give you a solution. So that would also be another way to show that a congruence is not solvable. So that's, did I do an example of that in the videos? I think I did. Where I just use a complete set of residues to show that a congruence. That's something that's another trick, right? You know, trick in your bag of tricks. But you didn't have to do that to show this how many solutions. Everybody did fine showing that. But if this is a really complicated expression, you can show that it doesn't have a solution by using a complete set of residues. I don't have all the homeworks in front of me, but you think of, the first couple of homeworks you had statements about divisibility. You didn't know what. So those are definitions. So I give you, short proofs that check if you understand a definition, key definition that we use, and then computational type problems. You'd be able to do those type of things. Does that answer most of your questions? Do you have any other questions about the midterm?
Will homework 6 be due on the 2nd?
Yeah, that's another question. Yeah, I'd rather you guys study, right? So I would probably at least give an extension, probably to the end of the week. Are we meeting the next? We're not meeting the next week, are we? Yeah, I'll probably make that homework 6 due the end of the week. I don't know when.
That's the 4th.
Yeah, that's not good.
Yeah, Wednesday.
It doesn't really. The thing is, it doesn't really. I want to have them graded so that we can discuss them. By the time the next time we meet. But I'm not sure what was the other meeting days? 14th. Yeah, I don't care. I can make it due the next week. I don't care if it takes 2 weeks or whatever. So I'll definitely extend the deadline for homework 6. So you won't have to be. It might be helpful because I'll be with you guys on the first. If you had questions, you can still meet up maybe after the exam or something. Okay. Any other questions? We drag this out now. Glad I didn't let you out a half hour early.
I was looking at that.
Nice. So, we're good? So, yeah.
Oh, I was looking at the syllabus. What is the grading scale? You have the relation here.
You have to be determined.
Yeah, it has to be determined.
Yeah, there's different philosophies on how to grade a graduate level class. One philosophy, I had my PhD advisor, he didn't like grading stuff, so he just gave everybody an A. Which, like I said, one method, but so I want to see. You guys are doing great on homeworks. I think everybody has an A on the homework average so far. But I think we'll start to differentiate maybe scores when we see a midterm, and so I don't want to. I didn't want to set it in stone. So I've never taught this level class. But what I try to do is be fair. I try to get fair homework assignments, give you chances to prove what you know, give you a chance to prove what you know on midterms in a fair way, grade consistently and fairly, and I think if you know what you're doing, you should get an A, right? If you don't know what you're doing, you shouldn't get an A. It's my philosophy, right? So I'm not going to grade on a strict 90 to 100 A, whatever. It might work out that way. But I don't mind giving everybody an A. If everybody gets an A, everybody gets an A. So, but I really wanted to kind of just wait and see. I know Dr. Whitaker's he's already put his out there, he's pretty broad. that, real analysis is tough. I mean, you guys. It's what it is. I had grad classes.
Clearly.
I had an abstract algebra class, and the guy is like, genius professor. I go into his office hours and he'd go, and I just think about it some more. He would never, and I'm like, well, I don't know what I'm doing, and so he gave everybody an A. So I mean, it's just kind of like, I think I got like a 60% on the midterm. Hey, so but I don't think he was being fair, So I think, but nobody seemed to complain because everybody ended with an A. So that's not my philosophy. I want to give you a chance to show what you know and be fair about it. And so hopefully you feel that way when we're done the whole thing. So any other questions?
I have a question. I didn't know if there's any way from what I've written here to make this pretty clear where I'm trying to prove it. This would either be even or odd.
This is the one.
Yeah.
All right, let me just wrap this up. Is that okay?
Yeah, that's fine.
All right, so I'll see you guys tomorrow.